Okay, two more amazing talks this afternoon. The first one by Jaroslav Trnka will tell us about non-planar on-shell diagrams.
Okay, thank you very much. For bringing this nice workshop together, inviting me. These people are still coming, but let's start. So this is kind of more broad general talk about non-planar on-shell diagrams. I explain what these objects are, but in mathematics they would be called Playbig graphs, non-planar Playbig graphs. And this has been something I've been pursuing in certain directions for some time, but there are many open questions. It's still very early time to actually understand more general structure of these objects. And this is done in collaboration with my two students, Taro Brown Umut Oktem, Shruti, who's in audience, and Melissa Sherman-Bennett, who's a faculty in math department at Davis. And there are also related works which touch some of the aspects of this non-planar story. So I will mention some of them in the talk. But as I learned relatively recently, there is a relatively rich math literature which use these non-planar diagrams in certain, or at least from certain point of view, to solve some different problems, but they appear also somewhere. So I hope to learn more about their role and if they are related to some of the questions I will pose here. Okay, so the motivation to consider these objects is this relation between scattering amplitudes on one side and Grassmannian geometry, positive Grassmannian on the other side, which is for the planar case. So the amplituhedron as a kind of geometric picture for amplitudes in planar n equals 4 super Young-Mills. It's also a planar object. By planar, I mean that all diagrams, all building blocks, everything can be drawn on a disk, and you have some ordering of external particles. And these on-shell diagrams, which actually predate the amplituhedron, are very useful building blocks for the amplitude, and they also appear to be triangulations of this object that we heard about already before, and will be more talks later this week. And in mathematics, they are known as Playbig graphs, planar bipartite graphs. And this connection is not just through using the same diagrams to solve different problems, but they are actually intimately connected in a sense that we use the information from math, from the study of these Playbig graphs and positroids to actually calculate on-shell diagrams and amplitudes on the other side. And so what is the role of these diagrams? Kind of a little more specifically on the physics side. So in physics, we are calculating the tree-level amplitudes and loop amplitudes. So the amplituhedron gives either the tree-level amplitudes or something called integrand of loop amplitudes, which is the object that we are supposed to integrate to get the final amplitudes. And the on-shell diagrams appear here as certain expansion building blocks for that, either at tree or at loops. But they also appear at the same time as something called cuts, which are integrals of this object, but on some simple contours, which still gives the same object. And once you integrate this, and you actually get some very complicated transcendental functions, they also play a role as the coefficient in front of these transcendental functions. So there are some algebraic functions, building blocks, and they appear in different contexts in this amplitudes word. Yeah. And this is from the physics point of view where they appear, and from the mathematical point of view, they appear as being connected to cells in the positive Grassmannian and have interesting combinatorial and cluster algebra structures. I will review a little bit of that later. Now, our motivation is to study graphs which are not planar, so objects like this. In mathematics, the positivity, which was the guiding principle for these Playbig graphs, is lost. There is also no known combinatorics relation to permutations. And at least to my knowledge, we don't know about any special structures, at least in general. In some particular cases, perhaps, but general about drawing these graphs and say if they are related to some interesting mathematics. On the physics side, the loss of planarity also causes some harm. we don't have any good definition of loop integram, despite this has been kind of work on progress from many directions, defining the non-planar loop integrand with some success. We don't have any amplitude hedron, and we don't know any hidden symmetries, which also drove a lot of the progress on the planar side. However, the connection to amplitudes partially still persists. So if we take the non-planar loop amplitudes and there is some object that we integrate, then these non-planar diagrams still play a role as cuts certain special integrals over special contours. And once we integrate, there are also some complicated functions with prefactors, and they also play a role of these prefactors. So the connection to physics survives. These objects still provides some useful information about the physical amplitudes, despite we don't know how to actually build the amplitude out of them. Yeah, which is also connected to this question of non-planar integrand and so on. But they contain some information about amplitudes. They are relevant objects on the physics side. So our goal, like a long-term goal, is to study these non-planar objects. On the mathematical side, find some combinatorial or geometric structures associated with these diagrams. And on the physics side, explore new symmetries, hidden structures, tell something about non-planar integrands and amplitudes. And maybe, hopefully, also in this direction back, the thing that we already know about them from physics may point us to something which is hidden on the math side. OK, so I will start with reviewing partially the planar story, which a lot of you are familiar with, and many people have been working on that. But just to set the stage. So yeah, so I apologize for being kind of very brief here and not very precise, but I will just review what we will need for the talk. So we start with the Grassmannian GKN space as a configuration of k-planes in n dimensions. We associate a k by n matrix modulo GLK, and the positive Grassmannian is a subspace here for real, in the real space, in the real Grassmannian, such that all ordered minors, k by k minors, the maximal minors, are positive. And this is a space with boundaries, with interesting geometry. The boundaries of this space correspond to a sequence of minors when we take adjacent columns of it, consecutive columns. Now, the cell in the positive Grassmannian is given by a list of vanishing minors. Now, for purpose to visualize, or at least for me, what these spaces are, it's convenient to think about this k by n matrix. So originally, we would think about it as some k-plane in n dimensions, but I can also think about it as endpoints in k-dimensional space. So then it's useful actually to think about it as projective space, so rescale the columns of this matrix. And then the simplest non-trivial example of Grassmannian G2n, so 2 by n matrix, would be endpoints on a line. And the convexity, the positivity implies convexity. It here means for this case that these endpoints are ordered 1, 2, 3, 4 up to n. And this guarantees that the 2 by 2 minors, order 2 by 2 minors, are positive. For G3n, this generalizes to endpoints in a plane. So this is an example of G plus 3, 6. This is configuration of 6 points in a plane. This is a convex configuration. And if we have this configuration, this guarantees that all 3 by 3 ordered minors are positive. Now, the top cell is the space which is maximal dimensional. So here we have top cells. There are no constraints imposed on these points. No minors are 0. And the boundaries, the lower dimensional cells, are obtained by specializing these configurations and pushing some of the points to special locations by setting the consecutive minors to 0. So for example, for this G plus 3, 6 points in P2, we start with this configuration, and then let's say we send miner 4, 5, 6 to 0, pushing points 4, 5, 6 to be on a line. And in addition, we can set 2, 3, 4 to 0. These 3 points are in a line. Then sending another consecutive miner to 0, we merge points 3 and 4 into being on top of each other, and sending another miner to 0, we can remove point 3 from the picture completely. These typically sending these miners to 0 have more solutions. I'm just showing one of the solutions, but there are more solutions how to do it, correspond to different configurations. Now it's a good question how to actually parameterize the matrix which corresponds to such a configuration. Let's say this one. So we can just from the picture read off the dependencies. For example, 3 and 4 are on top of each other, so the column 4 is proportional to column 3. 5 is spanned by 2 and 3. 6 is spanned by 5 and 1, and we can write these linear relations between them. But the parametrization of this G36 matrix that we get from just doing it naively like that doesn't make manifest that all the maximal minors are positive. Yeah, it's not clear how to choose these variables such that it makes manifest that all the ordered 3 by 3 minors are positive. So the question is, can we parameterize this matrix in some manifestly positive way? And that is connected to the story of the Playbig graph, introduced by Alex Postnikov in 2006 in this setup. And the Playbig graph gives a positive parametrization of this cell in the positive Grassmannian. So for example, for this configuration, this is a top cell in G+2,4. This will be a Playbig graph which is associated with that. And now to go from the graph to an actual parametrization of the matrix, there is a procedure. You choose so-called perfect orientation, which is adding arrows to all the edges of the diagrams with some rule, such that one type of vertex has one incoming arrow and 2 outgoing, and the other type of vertex, there are 2 types of vertices, has the opposite. And then you associate variables either with edges or faces. Here we do edges. And these variables modulo some rules that you can set some of them, fix some of them to 1 or some other value. There is a rule which provides you the entry of this matrix, particular entry Cij, in terms of path through that graph and taking the products of these variables. Okay? And once we do this so-called boundary measurement for the graph, we get the parametrization of the C matrix in terms of these H variables. And then the claim is that if we fix signs of these H variables, this makes manifest the positivity of all minors. Okay, so that's the boundary measurement and positive parametrization of the graph. Now, there are for special set of graphs called reduced graphs. I will say more on the next slide. There is also connection between these graphs or these cells in the positive Grassmannian, which are connected, and permutation of n labels. So we can actually reduce the information about the graph or about the configuration to just a set of permutation of labels. So very kind of very economic way how to label the diagram. And this is one of the property which will be lost once we go to the non-planar setup, and the one which is one of the big open problems, at least the way how I see it. Now, we saw that once we are in some cell in this positive Grassmannian, it's easy to access the boundaries. It corresponds to sending the minors to 0, which means merging the points or putting them in special locations. So at the level of the diagram, once I go to this lower dimensional cell by setting some minor to 0, this corresponds to setting one of these H variables to 0 that were here on the graph and removing the edge. So we are erasing the edge which carried this H variable, and we are getting a simpler graph. So the graphs kind of carry this very simple structure of the minors and going to the boundaries by erasing the edges in corresponding diagram. Now, about these reduced graphs, which will play an important role for us. These are, roughly speaking, these are graphs which don't contain internal bubbles. So they somewhere inside the graph, they don't contain the bubble. And there is a precise rule how to detect that given diagram doesn't have bubble, because sometimes you can have this internal bubble, but then you use certain identity moves which don't change the cell of the Grassmannian, but they change the graph. It looks different, but they don't change the cell in the positive Grassmannian it corresponds to. And the appearance or the presence of the bubble cannot be completely visible. So there is a definite rule how to tell if the diagram is reduced or not. And these identity moves, which is a merge expand, so once you have a sequence of these vertices of one color, so like here you can merge them and expand in kind of the opposite channel. And there is also more intricate square moves. So once anywhere in the diagram you have this box with this coloring, you can always flip the coloring to the other black and white. So this is black vertex, despite it looks blue here. You can flip the color of vertices. And these moves also don't change the permutation associated with the graph. And they don't change the cell in the Grassmannian. Okay, so now going from the point of view of scattering amplitudes, so let me a little bit set the stage very quickly. It was done in some of the previous talks, also in Anastasia talks, had a very similar introduction. So on the physics side, we are interested in this mathematical object called scattering amplitude, which is related to a quantity called cross-section, which that is directly related to some probability in particle scattering, that for initial state we get certain final state. So we are interested in this object. This is in general complicated function of kinematics of many parameters. It's something we expand in perturbation theory. We get some expansion. In this case, we are interested only in gluon amplitudes in one particular theory called planar, or not necessarily planar in this talk, but n equals 4 super Young-Mills. And the amplitude carries two labels, n and k. The first denotes the number of external legs in the amplitude, number of particles in the scattering, and the label k is so-called helicity number, which runs from 2 to n-2, and it's related to helicities of these gluon particles. And in physics, we also use notation MHV. This is for k equals 2. This is shortcut for maximal helicity violating, NMHV, k equals 3 next to, and then so on. And then on the other side of this spectrum, when k is n-2, we call it MHV bar. Now, as I said before, we distinguish between the 3Ks, kind of the leading term in the perturbation theory, the simplest amplitudes, which are just rational functions, and the loop amplitudes, which are integrals of rational functions. And instead of using the standard procedure of Feynman diagrams, we have different building blocks, which are exactly these on-shell diagrams. Now, in physics, these on-shell diagrams are obtained from amalgamation procedure, which is gluing together some elementary building blocks called 3-point amplitudes, which are associated to these two types of vertices, the white and the black one. And there are some rules that we glue them together into some bigger object. There are expressions for each of these vertex, and we kind of multiply all of them. And in the end, what this on-shell diagram means for us in physics, it's some function of kinematics. So it's function of some variables called lambda, lambda tilde, spinor helicity variables, and possibly some other parameters. Now, these on-shell diagrams provide certain information about the amplitude. At 3 level, we have recursion procedure, how to build the amplitude from these diagrams called BCFW, also mentioned in other talks already. But only some of these special on-shell diagrams appear here. Yeah, we don't really exploit all set of on-shell diagrams. They are kind of a special subset. But all diagrams actually play a role in loop amplitudes, as I said, as the coefficients of these complicated functions after integration, or some special integrals on the amplitude called cuts, then all of them play a role. So all on-shell diagrams actually appear as some information in physics. But only a special subset appears in this expansion for tree-level amplitudes. Now, for these kinematical variables, the spinor helicity variables, they are a convenient way how to parameterize massless particles in 4 dimensions. So normally in physics, we associate 4-dimensional momenta, 4 momenta in 4 dimensions, but we can repackage the components in 2x2 matrix using the fact that the determinant of this 2x2 matrix is actually p squared. It's a square of the momentum. For massless, we get 0. And then we can write this matrix as a product of two vectors, spinors, lambda and lambda tilde. So all the information about the momenta we can package in 2 by n matrices, lambda matrix, when for each particle we have 1 column, and lambda tilde matrix, when for each particle we have also 1 column of these 2 types of spinors. And the momentum conservation, the fact that in the process the sum of all momenta is 0, corresponds to the fact that the lambda and lambda tilde planes are orthogonal. Now know that this is n-dimensional space where they live, the space of all particles. So in this n-dimensional space, these lambda and lambda tilde 2 planes are orthogonal. So in the formulas, we will denote it like some delta function that the argument needs to be 0 in order to have non-zero expressions for amplitudes. Okay, now, so this was in physics. So these on-shell diagrams corresponds to some information about amplitudes, and there are some functions of kinematics. For this diagram, this would be the function when these brackets in the denominator corresponds to some 2x2 determinants of these lambda spinors in this case. And on the mathematical side, we have this connection of these Plaby graphs to the cells of positive Grassmannia. Now, this is not all. If it was just this would be just connection between graphs. But we can reproduce this function calculated here as certain integral over a dlog form on the cell in the positive Grassmannia. So that's the main connection here. And there are certain delta functions which will relate the h variables or other variables here with these kinematical variables on the other side. So this is the content of these delta functions. But let me first talk about the dlog form, this d omega, which sits here inside. So this is a form with logarithmic singularities on the boundaries. So whenever I approach some boundary, when some parameter x is 0, I generate dx over x as the singularity. So for the cell of the positive Grassmannian, we can write it in 2 equivalent ways. We can either use these h variables, and then it's just d alpha over alpha for all h variables in the given graph. Or we can also use an invariant top form, writing it in terms of minors of this C matrix. And then it's a product of all consecutive minors of this k by n matrix, and we have to mod by GLK. So for these simple examples, for the top cell of G2n, this, the G26 in this case, this would be the top form, or the dlog form corresponding to the top cell. For G36, it's this one. You see a very simple structure of these minors in the denominator. And then, once we go to a lower dimensional cell, we start to merge points or put points on lines. We are taking residue of these forms on the corresponding minors being 0. Now, about these delta functions, the motivation to even introduce these Grassmannians in the first place in physics is to think about this condition of the lambda and lambda tilde plane being orthogonal and trying to linearize it. So instead of condition between lambda, lambda tilde, try to make it a condition on lambda and lambda tilde separately. So for that, we introduce a k-plane C, and we force the C to contain lambda and be orthogonal to lambda tilde. Okay, so this is something which also appeared in previous talks. before. So the physics result, the claim or the conjecture, proven conjecture, is that this function in physics is reproduced by this dlog form here and dressed with these delta functions. Now, these delta functions is 2n conditions on the parameters of this C matrix. Out of these 2n conditions, 4 of them turn into this momentum conservation, into this condition between lambda and lambda tilde, and 2n minus 4 of them become conditions of the h variables alpha. Now, the general Plaby graph is d-dimensional, contains d h variables. So there is something very special about d being 2n minus 4, because in this case, all the h variables are solved for. So this alpha star is a function of the lambda lambda tilde. So if we have d equals 2n minus 4, we can solve for all h variables. If d is not 2n minus 4, either some of the variables are still there, so they are not solved for, they are free parameters, or if the dimensionality is lower, we have extra delta function which start to impose conditions on lambda lambda tilde. So these special cells in positive Grassmann, these special on-shell diagrams which saturate this 2n minus 4, d equals 2n minus 4, are called leading singularities. For the reasons from physics, they correspond to kind of maximal codimension singularities we can do on the loop integrals. And they are 2n minus 4 dimensional cells. And we solve for all these h variables, and we are getting just function of lambda lambda tilde. And these are the diagrams which are important as the building blocks for 3-level amplitudes. But they also solve as kind of the leading singularity or maximal codimension cuts of loop amplitude. So this is a very special set. Now, it's not enough just to say that the cell or the graph must be 2n minus 4 dimensional. It also must be reduced. So it cannot have any internal bubble. So here is an example of these are all reduced diagrams. So these are all leading singularities, but this one is not. Despite, if you just count dimensionality, it has also dimensionality, the correct dimensionality is 6. But here we have, if you calculate the form, it has one more extra alpha, one more parameter which is unfixed from this delta function, but at the same time imposes the condition on 3 and 4. So there is a constraint on lambdas. The lambda 3 and lambda 4 are proportional. This bracket is 0. But at the same time, one of the alphas was not solved for. And the reason for that is that this is not a reduced graph. There is an internal bubble that you can expose once you use these identity moves. So this is not a leading singularity, but these are leading singularities, because these guys are reduced and this one is not. Okay, so this is the planar summary. So we have these objects, we have this connection, how to calculate it from the dlog forms on the positive Grassmannians and these delta functions. Now we can go kind of farther in the planar story beyond these diagrams. We can define new variables called momentum twisters, which get rid of these momentum conservation, trivialize it. In these momentum twister variables, the momentum conservation is automatically implied, despite for these lambda lambda tilde, it's a constraint we have to impose. And these momentum twisters, this is exactly where the amplituhedron lives, when the collection to these on-shell diagrams kind of glue together into some bigger object. But the amplituhedron can be also defined directly in the spinor helicity space. It's called momentum amplituhedron. But for both cases, the important is the ordering. We need to have an ordering of particles 1 to n to be able to define these objects in the first place. So now we turn to the non-planar diagrams. So for these non-planar diagrams, the ordering is obviously lost. Yeah, there is the external legs are not ordered on a disk. We don't know You cannot associate reasonably any ordering with them. As I said before, they are needed for physics. They provide some information about the non-planar physics amplitudes, but they are no longer building blocks. So we cannot glue them, or we don't know how to build the amplitude out of them, but they provide some information, some cuts. These coefficients of polylogarithms are given by these on-shell diagrams. But they are still simple functions, and we know what they are. We can calculate them. So it's a great laboratory for studying non-planar amplitude. So that's the physics motivation. And this, for me, the mathematical motivation is that we can still take these diagrams and associate some symmetrics with them. We can use the same procedure as in the planar case. We are losing positivity or orientation on these graphs, but we can still try, or the goal would be to see if the positivity and other things are replaced by something else, some other properties, some other structures. Now, the reason why to be optimistic, maybe this is just wishful thinking, but if we think about this non-planar graph as a symmetrics, using the boundary measurement as some sort of object in the Grassmannian, no longer positive, and we go on the boundaries, so we set some h variables to 0. We can still use h variables here. Eventually, we hit planar diagram. Because, for example, for this one, you have to erase 2 edges, and you get some planar diagram, and the planar diagram corresponds to a cell in positive Grassmannian. So in a sense, if you think about this as an analog of a top cell of positive Grassmannian, which is not positive anymore, on the boundaries, it contains a bunch of lower dimensional cells, which are cells in positive Grassmannian, but with different ordering. The ordering changes, but they are somehow glued together in a new way, which doesn't respect this ordering. Okay, so kind of how bad this space can be if it has these nice positroid cells on the boundaries. Now, the one thing which will be important for our discussion is the form. We will learn a lot from this canonical form, from this dlog form, which we can still use the same formula, which gives us the form in physics. We can still use the same Grassmannian formula. We still use the same dlog form in terms of h variables. We use the same delta functions, and we are getting some function of lambda lambda tilde. Now, there is no single top form or the maximal dimensional cell here. There will be multiple of them. And when we write this in terms of minors, it's not just a simple formula in terms of minors. Now there are mole poles, there are some numerators. It's kind of a little bit more complicated. And there is no ordering. So the question stays if for these objects there is any analog of the positive Grassmannian. Now, as I learned relatively recently, there have been these non-planar graphs, non-planar Plaby graphs, have showed up in literature in recent years in different contexts. So I'm sure there is a lot of the questions I would like to pose have some partial answers or have some connections in these papers. Also in the talk of Thomas Lam, related things were mentioned. So these are all very likely relevant things to the goals here. So I hope to learn more about it in short time. So let's just focus on something specific. So let's look at G2n. So this would be the simplest case. We then look at G3n. That would be basically beyond that, things become more complicated. But these two examples of G2n and G3n are worth pursuing in the first place. So for the G2n, the leading singularity in physics, and which corresponded to these reduced Plaby graphs, the top dimensional, are 2n minus 4 dimensional top cell. In the planar sector, when things are ordered, this was the canonical form. This form was actually known in physics literature for 40 years now. It's called Parke-Taylor factor. It corresponds to some simplest amplitude. The reason why I can directly go from the minors here to the spinor helicity variables where the amplitudes live is that the condition is that on the C matrix, these are 2 by 2 minors of the C matrix, is that the two-plane C contains two-plane lambda. So the C is just lambda. And these brackets in terms of lambda spinors are just the 2 by 2 minors in terms of C. So for G2N, there is only one matrix, C or lambda is the same thing. The lambda tilde basically doesn't make any appearance. It only appears through this momentum conservation. Now, the Grassmannian G2N, not the positive part, but the full Grassmannian, is completely tiled by positive parts with different orderings, which is kind of clear because you have endpoints on a line, and for given point in this Grassmannian G2N, you always have the points ordered somehow. So if you take a collection of all these orderings, they kind of tile the whole Grassmannian, which is not true for any other, for G3N and beyond, it's not true. Now, the canonical form for each of them, just given by this formula for different orderings. So sorry, I might be switching between these two different notations. They mean the same thing. And we often refer to this form as Parke-Taylor factor for these historic reasons in physics. Now, if you just ask what are all possible dlog forms you can write on G2N, then they must be linear combinations of these Parke-Taylor factors with different ordering. So these Parke-Taylor factors, in other words, these forms on the positive parts of G2N with different orderings form a basis of all possible forms. Yeah. There are other forms that you can naively write, but they don't have logarithmic singularities. For example, this form, when you have kind of two separate set of indices, 1, 2, 3, and 4, 5, 6, actually does not have logarithmic singularities. If you go on one of the boundaries, then you produce a double pole. So, so these Parke-Taylor factors give a basis for all dlog forms. Now, if we now consider this non-planar diagram, like this one, for G26, we dress it with H variables, we solve the delta functions, we solve for the C matrix, here I display C perp matrix, we get some solution in terms of lambda only here. And the form of the C matrix, how the solution look like, you can see that there are kind of pair or triplets of different labels in each of the rows, suggested a new formula, new kind of simplified formula, faster way how to calculate this form, which was in this paper we already wrote several years ago. And it's based on the method of triplets. So for each G2N graph, there are always n minus 2 black vertices, and each black vertex is connected through a chain of white vertices to 3 external legs. So this is special for the G2N. And this is how you read of the triplet. So for this black vertex, you write the names, the labels of the 3 external legs which are connected to it, and you have collection of n minus 2 of them. And using these triplets, you can actually calculate directly the form. And you take this matrix, there is a certain procedure, you delete 2 of the rows, and then you take a determinant of these metrics and you divide by a 2 by 2 minor, which corresponds to the, columns, to the columns that you deleted here. And you divide it by the product of 2 by 2 minors corresponding to these triplets. Okay, so there is a very simple formula for that you can use for any graph. And once you evaluate this form, so this is a form on this top cell in the G2N, you get a lot of poles, many more than 6, which was for the positroid, and you get some interesting numerator, square. Yeah, so there is some polynomial square in the numerator. So this is dlog form on this non-planar G26 on-shell diagram. And the numerator will play a crucial role later. Now, as I said, these Parke-Taylor factors with different orderings form a basis, so I can take this form and just expand it in terms of these Parke-Taylor factors. And there is a very straightforward procedure how to tell which of these Parke-Taylor factors are there in the expansion. They are all Parke-Taylor factors which are consistent with some orientation of these triplets. So 1, 2, 3 should be oriented in this order in all of the Parke-Taylor factors, 2, 5, 6, in the same ordering and so on. And here you can reorder each of the triplets you can reorder. You get a different set of Parke-Taylor factors because you are changing the ordering, but the sum is always the same. Yeah. So different orientation, different expansion, same sum. And once you then combine it back, you get this formula as we calculated using the first procedure before. Yeah, these Parke-Taylor factors are not all independent, as you can see also here, because different expansions give the same formula. They satisfy a lot of identities, yeah, including, for example, the simplest one, which we call U1 decoupling identity. If you take n points on this line and you take one of the points and start to shuffle it through, then the sum of these Parke-Taylor factors is 0. Note that in this way of doing this, in this expansion, you would actually, term by term, generate spurious singularities or spurious poles. For example, the 1, 6 pole, which will appear in some of the Parke-Taylor factors, is absent in this formula, and they will kind of cancel once you do this sum. So this formula makes the logarithmic singularities manifest, but doesn't make the pole structure manifest. While this one has all the correct poles in the denominator manifest. But the fact that it's a dlog form is not that very obvious, because if you just look at the denominator and calculate some of the residues, you start to generate multiple poles, and they will be canceled by the numerator. The purpose of the numerator is kind of cancel these poles. Now, the formulas, these forms, these canonical forms, also don't change under certain identity moves. One of the moves is a regular square move that we know from the planar case. They actually do change the triplets, but they don't change the form. So the triplets are some sort of not very invariant way how to label the diagram modulo moves. Yeah, they give a fast formula how to calculate it, but they are not invariant way to label the diagram. But these are not the only moves. There are also other moves which were found in this beautiful paper under the name of the sphere moves. You can take the diagram, you can actually draw it on the sphere, and there are sequence of moves which will change the triplets, but they are not changing the form for the diagram. Okay, so beyond the square moves, these are the only moves in addition to merge expand in the planar case, but in the non-planar there are already new moves. And as I will mention later, up to G28, these are the only moves which are there. Yeah, just doing the numerical check. There are no other ones. So maybe it is true that these are the only moves that we have actually here. Okay. So our goal is to find some classification of all of these top cells in G2N, basically generate all triplets. All of them are 2n minus 4 dimensional on-shell diagrams, and the top cells would correspond to some reduced set of these on-shell diagrams. So that was one thing we have to do here. We have to define what does it mean reduced, because in the planar case we had this definition when there are no bubbles, and there was a rule how to tell that the diagram has no bubbles, but this definition doesn't necessarily extend here anymore for the non-planar diagrams. So here we use some knowledge about the forms. So the conjecture that we can make here, which is kind of supported by our, it's not proven, but we check it up to G28, that all non-reduced 2n minus 4 dimensional G2N on-shell diagrams have at least one vanishing Plücker coordinate. Okay, so this is an analog to what I showed before here. That okay, if I get how far? Yeah, this one. So this is the analog of this. Yeah, this also has the correct dimensionality, but the Plücker coordinate 3, 4, the minor 3, 4 is 0. And there is a bubble in the diagram, which kind of is responsible for this extra variable here. So this is also not reduced. Now, in the non-planar case, in principle, we can also have some diagram, like this complicated diagram, which has the correct dimensionality, but there is some secret polynomial condition which is imposed on that matrix in the diagram. And this will actually happen once we go to G3n and beyond. Yeah, these type of things will happen, but for G2n it doesn't happen. So whenever the diagram has zero canonical form, it actually corresponds to the fact that there is a zero vanishing Plucker coordinate. Okay. So there are no, so all of the diagrams which have non-zero canonical form are top cells from this point of reduced diagrams. So, so in any diagram produced by these triplets, either it's a reduced diagram or it's a diagram which has vanishing Plucker coordinate, like ij is 0. Two of the legs are in the same vertex. Okay, so then we can actually also count how many of these top cells are there in G2n. So for G24, it's just 3. There are just 3 different orderings of this box diagram. And then it grows like that for G25, G26, G27, and G28. Maybe there is some numerics, but the sequence finder definitely doesn't know these numbers. Now, as I said, up to the G2A, there is no new identity moves beyond this square move and the sphere move. We can also count all different types of top forms. So this is modulo permutation. Yeah, if you just look at the structure of the top form, how it looks like, you consider that different permutations is kind of the same thing. How many different types are there? So there is only one for G24. It's always the same top form, just with different orderings. G25 is 2, 5, 14. Then we got excited, but it was 66 afterwards instead of 50. So, okay, so yeah, the sequence finder also doesn't know that. Yeah, so, but related to this question is also a question about labels for the top cell. So as I already said, the triplets is not a good way how to label it because square move changes that, sphere moves change that. Yeah, is there any analog of the permutation which would be invariant under these identity moves? Yeah, so that we don't know. That's an open question. So now the second thing is about the numerators. I said that these numerators of these forms are important. So this, I don't know fully how to formulate it in math. Yeah, there is some sort of physics flavor that I have to add. But these numerators are, have some very special properties. So they are connected to something which we call poles at infinity. So now if we consider this on-shell diagram as gluing together of 3-point amplitudes in physics. So in addition to the external legs, there are also these internal edges, and they also carry momenta. Now for these diagrams, which we call reduced, these momenta will be fully fixed in terms of external kinematics. They will be just functions of lambda, lambda tilde. Yeah, they are solved from on-shell conditions on these momenta and momentum conservations. So we can solve for them. If we solve for them, you get expressions like that, so that the momentum L1 is lambda 1, lambda 2 tilde, and there is a minor 2, 3 in numerator and 1, 3 in the denominator, and so on. So everything which is in the numerator, it corresponds to erasing an edge. If we send it to 0, we just erase a given edge. We get a simpler diagram, and it corresponds to poles in that given canonical form. Now, there are also things in the denominator. They are not poles of the canonical form. Yeah, they don't show up in the canonical form as poles because all the poles are related to erasing edges, setting edge variables to 0. But from the physics point of view, they set these momenta to infinity. They kind of blow up the loops. And yeah, we call it poles at infinity because the L goes to infinity in the given diagram. So these poles at infinity are actually very interesting. They are not associated with edges, but with cycles, because the cycle kind of tracks down where the pole at infinity is present, in which of the L's associated with each edge has this pole at infinity in the denominator. Now, for planar diagrams, they are always contained in a given loop, in a given cycle. They kind of don't propagate outside that cycle. But in non-planar diagrams, they kind of propagate everywhere, which must be related also to the fact that the cycles are not canonically defined, like in planar diagrams. So these poles at infinity, in this diagram, all of these momenta L will have the same pole at infinity, 1, 3. Yeah, sorry, it should be 1, 3. I don't know. This is kind of moved these circles here. Now, these poles at infinity are actually relevant for, they do appear eventually as poles in some lower supersymmetric amplitudes when you take these dlog forms and decorate them with some extra factors. Okay, but now what is the connection? The pole at infinity, this condition, the analog of this 1, 3 here, for, that we would get in the diagram, actually it's the same condition on sitting on this pole at infinity as the thing that we get in the numerator. So in this diagram, if you solve for L, this factor would show up in the denominator of this expression for L. So sending this expression in the numerator to 0 would blow up this L in the diagram to infinity. So there is a connection between like solving for these momenta and seeing where the poles at infinity are located with the numerators of these forms. So at least I don't see any a priori reason why it should be like that, but we checked on many examples that all zeros, it's actually not just some, all of the zeros of these forms are poles at infinity in the diagram. And this should to extend beyond G to N. So we have some G36 and G37 examples when exactly the same thing happens. Now there is a little bit of subtlety because here these are 2 by 2 minors of this G to N matrix. Once you go to G3N, then this is lambda and lambda tilde. These are it's no longer the minors of the Grassmannian. You have to solve for that in terms of lambda lambda tilde. But the same thing is true. Once you look at the omega, in terms of lambda lambda tilde at the numerator, the same thing which shows up in the numerator is the pole at infinity of the corresponding diagram. So there seems to be this correspondence, which anyway, it's kind of mysterious how these two things should be related. So let me now say something a little bit about G3N, the things which are understood here. So obviously, going from G to N to G3 and Gkn is more complicated because, as I said, even starting G36, the Grassmannian G36 is not tiled anymore by just the positive Grassmannian G plus 36 with different orderings. So if we consider this configuration of points in a plane, there is no ordering. Obviously, they are not ordered. So we have to consider things beyond just different orderings of the convex configuration. Also, the C is not lambda. So once we talk about this form omega, in physics, we have to actually solve for these variables in C in terms of lambda tilde and get a formula for lambda lambda tilde. So the relation between the forms and the expressions of the lambda tilde there is some work to do. Yeah, not like in G2N when it was literally the same thing. Now, also a reminder that if we talk about these objects which are relevant for physics, these leading singularities, they are 2n - 4 dimensional, which happen to overlap with the dimensionality of the top cell in G2N, no longer for G3N. Yeah, so we are talking about some lower dimensional cells. Okay, so with that in mind, let's go back to the BCFW recursion relation for tree-level amplitudes. I said that only a subset of these leading singularities, these on-shell diagrams, reduced on-shell diagrams of a correct dimensionality 2n - 4 actually appears. It's a special subset. For G plus 3n, we can actually kind of see directly what is special about them. So if you look at 2n - 4 dimensional cell in G plus 3n, this corresponds to a configuration of points on 5 lines. Yeah, this is just what is the geometry of these cells. But the BCFW one have only kind of it's a reduced version of that, where all these points are only on 3 of the lines, not 5. So it's a special set. We cannot see it already here. The BCFW are more special than the generic cell of this dimensionality. Now, it's easy to actually see how you would generate them. So this is a procedure at the level of the on-shell diagrams. The recursion relations always recurses a product of lower loop amplitudes. There is a 5-point amplitude here and 3-point amplitude here, and add some extra BCFW bridge. And you sum over all possibilities how to divide the legs in these amplitudes to the left and right. At the level of these configurations, let's just look at this diagram. You start with two 4-point amplitudes, this one and this one, which means 3 points on this line, 3 points on this line. Actually, this intersection point corresponds to this middle line here between them. And then you are adding this bridge on top of that, which means moving this point 6 in a direction of 1. So this is the final geometric configuration corresponding to this Plaby graph here. Now you can do it for all of the cells. You can also solve it in general. For the general solution for n-point and MHV amplitudes, cells in G+3n corresponds to summing the corresponding canonical forms for the cells which look like this. Yeah, configuration of points on 3 lines when you fix one of the point here in the center, and then you distribute it respecting the canonical ordering. So this is the standard story, known for a very long time, actually predates even the stuff with the on-shell diagrams. So let's now do something unorthodox. Let's do these recursion relations, but now with a non-adjacent shift. So instead of adding this bridge 6 and 1, I add the bridge, different bridge, 5 and 1. So it's not between adjacent legs, but non-adjacent legs. So now immediately I start to get non-planar graphs, yeah, in this recursive procedure. Now we can actually look what it does at this configuration, because this is a planar graph corresponding to this, the same configuration. But now we did the bridge 5-1, which moves 5 in the direction of 1. So this is the configuration that we got. So this is some configuration in G36. Now here we can associate, so one of the minors is 0, because 1, 2, 3 is on a line. And we can read off the signs of all the other minors. So many of them are still positive, but some of them are negative, and some of them have unfixed signs. Yeah, so they don't have fixed signs from the picture. While in here originally, all of them were positive, and this minor was 0. Okay. Now we can actually go farther. We can take this picture, we can reinterpret it as actually adding one extra point on the convex configuration. So if you think about 1, 2, 3, 4, 6, this is a convex configuration, and we are adding 0.5 kind of in the middle of this 1, 2, 3, 4, 6 convex. And we can also then calculate a form. We can deform this into generic configuration where 1, 2, 3, 4 is not 0, and at this 0.5 to a pentagon. This is a dlog form for the pentagon, and we get a new form that we have to evaluate on this boundary, which again has some denominator, more poles, and has some numerator. And this numerator is again interesting. It would correspond to a pole at infinity if we now went back to the diagram and assign momenta, solve for the momenta, and so on. And here you see geometrically it corresponds to collapsing this triangle into a line. So this is kind of not allowed to do. And not only that, it's not a pole, but it also shows up in a numerator. It's kind of forbidden configuration. Yeah, why is it forbidden? I don't know, but this is what the form suggests. Now we can solve these recursion relations for these non-adjacent shapes. It's not so hard. And instead of having these points on 3 lines, we are still getting points on 3 lines, but they are not ordered. So they kind of the points can be anywhere on this line, not just here in the middle, and anywhere on this line, not just here in this segment. So there are 2 different orderings, basically. There is one ordering here, and there is second ordering going here. So this is still sufficiently simple kind of set of points, which has two different orderings. Perhaps you can associate two different permutations to it. This will definitely not generalize very far, but these are all BCFW cells that you can obtain. So the BCFWs were special in the planar case. In the non-planar, they are also special, and they correspond to well-controlled configurations. And yeah, it would be interesting to see if these objects in some way triangulate the momentum amplituhedron. It must be some strange triangulation because it doesn't respect manifestly ordering, but they are building blocks for the object. And the momentum space here is probably crucial because we cannot do it momentum twistors. We cannot even define them with the lack of ordering. And as I said, the numerator of this form corresponds to the pole at infinity for the corresponding on-shell diagram calculated in physics. So this mysterious connection holds here as well. Okay, so the last thing I want to mention is that one can actually start the problem of analyzing these cells very systematically. So in a very nice paper by Jake and his collaborators from 2016, they generated all on-shell diagrams for G36, non-planar, and they gave a list of them, including the forms in terms of minors. So for the above top cell, which in principle is not the one relevant for us in physics, but for the analysis of the geometry, it's the one to look at, and all 8-dimensional cells, which would correspond to these leading singularities. And this is how it looks like. There is a diagram, there is a form, and the thing that we did is to try to associate the geometries with the form. Just all the poles in the denominator should correspond to boundaries of these configurations. And for many of them, you can do it, and it looks like, sometimes it looks like adding a point somewhere inside of already convex configuration, but only a very small subset is actually allowed. Yeah, so this is allowed, and this is, for example, not allowed for some reason. This is not realized as an on-shell diagram, while this is realized as an on-shell diagram. You have also things which don't have only original points, they have new points, which are intersections of lines of original points. So the configurations become more complicated, but you can still identify them. There are some which have also square roots, so you are probably solving some quadratic equations. So here, these ones we don't know how to associate. Now note that here this chi, these are Euler characteristics. So these guys are not topologically poles, unlike the positive Grassmannian. So the Euler characteristic is pretty wild here if you look at these different examples. So that's not the thing which is preserved. Okay, and I'm basically done here. So just 30 seconds. We look at these non-planar diagrams. We would like to understand and classify them as some cells in the positive Grassmannian. Note that in the planar case, basically all of the convex configurations corresponded to the planar on-shell diagrams. There were cells in the Grassmannian. There are only special ones here. So some special non-convex ones are on-shell diagrams and others are not. So that's one of the unclear principles which selects these geometries to be representable as on-shell diagrams. Yeah, and anyway, in addition to this question in mathematics, hopefully the progress here will also solve some outstanding problems in physics, especially related to new symmetries, which we don't know for the non-planar sector of n=4 super Young Mills. It's suggested there are some symmetries hidden, but we don't know them. We just know the planar ones. And it might help also to define some non-planar version of the amplituhedron, and these objects will triangulate it. Yeah, but we don't know at the moment what it is. Now, as I said, there is a work on some exciting recent work which contains the new definition of the non-planar integrand. So the question is if it interplays with the things that we see here. And that's all. Thank you.
Let's take one or two quick questions. Very quick questions, somebody. Laura.
Yeah, so you said you want to classify top cells of G2N, and you defined reduced in terms of the non-canonical form. So then I was wondering, can you then identify the top cells by making sure first it's reduced, but also checking it has like the expected number of regions, or maybe you have to count regions minus crossings or something?
Yeah, so what we did was to start from triplets. They all generate some diagrams. and calculated forms for them. Now, many of these forms are 0, and they secretly corresponds to having a bubble inside. And because they have the right dimensionality, right number of H variables, so the bubble there must mean that there is some condition of Fluker coordinates. And everything was just a single condition of Fluker coordinates. So we factor them out, we get the remaining ones. Now there are these moves, so many things are related to each other. So then in the end, we identified what is really the set of the ones which are not related to each other. And they were given by some of the triplet formulas, but the triplets are not a good way to characterize it because they change under these moves. But these guys are on-shell diagrams, so I would say they are analogs of the top cell of the positive Grassmannian. But how to characterize them, yeah, I don't know. The thing that I would like to find is an analog of the permutation or something which would label this graph and this graph differently, and it would tell me why this labeling exists and some other doesn't exist. Or maybe if you really find good labels, then all of them would exist and all of them would kind of reproduce these numbers there in the formula. But that I don't know how to do. It's some generalization of this permutation, but unfortunately these triplets are not, they don't do it quite, yeah.
Okay. In the coffee break, Yara will be delighted to answer more questions. So let's actually stick to schedule. We meet again